In this lesson, we're going to be looking at projectile motion. So this is things moving in a gravitational field. So if we throw something straight up into the air and let it fall right back down to the earth, so a picture of what's happening here, so say this is the ground, we start with something maybe at some height and we throw it straight up into the air, and then it falls back down and goes back down to the earth. So that's a representation of what we're describing here. And what we're describing is, in this case, we're keeping it simple. We're just going to be looking at the height off of the ground and comparing that to how much time it has been in the air. And so our graphs are actually going to look like parabolas. They're going to look like this. And the reason is that if you, say, launch something into the air, might start right here, and then as it goes up into the air, time is passing. So we're going to be moving to the right. If we're describing the horizontal axis is how much time has passed, and so we're going to be moving to the right through time as this thing goes up and falls back down. And so it's going to make this curved path as it does that. So there's an equation. Now don't worry too much about why these parts of the equation are what they are. Once you get to calculus, you will understand totally why it is that like this negative 1/2 is here and the v sub 0 and the h sub 0, well, the h sub 0 we can get to in this class, but don't worry too much about why it is that this equation is the way it is. Once you get into calculus, then you'll learn why it is that this equation is what it is. But what we can do is at least apply it, even if we can't fully understand why the structure of it is the way that it is. So what we're going to say is you're used to seeing something like f of x. This is very similar. It's s of t. For some reason, we use s for the position of something. So s is the vertical position, the height off of the ground. And this is a function that uses t for time. So s of t is the position with respect to the time. So the height off the ground given how much time has passed. And that is described by this equation here. So it's negative 1/2 times a. Now I want to make a distinction here. The a here is different than when we have y equals ax squared plus bx plus c. A in this case is just whatever number's in front of x squared. This a right here is a little bit different. It's a for acceleration this time. So this is different than that a. This is the acceleration due to gravity on whatever planet you're on. So on Earth, that's 9.8 meters per second squared. If you have a bigger planet, things are going to fall down faster. If you have a smaller planet, things are going to fall down slower. We'll get into those calculations in a bit. Okay, then v sub 0, that is the initial velocity. So it's the velocity at time 0. And then h sub 0 is the height at time 0. It's the initial height. Let's look at a couple pieces of this equation before we get into an example. So the first question I have here is, why is the leading coefficient negative? Well, the leading coefficient, being negative, is going to make the parabola open downwards. And if you think about how things operate on Earth, it has to be that way. So, if we had the leading coefficient positive, that would mean something would fall like this, which would mean things are falling up. Well, that clearly can't happen. So if we're talking about things in a gravitational field on a planet, they're going to be falling down. So the parabola needs to be opening downwards. It needs to have a negative leading coefficient. And then also it says, why is h sub 0 the initial height? Well, if we look back to this equation here, if we think about plugging in 0 for time, so at time 0, right when we start our clock, this is, if we plug in 0, that goes away, plug in 0 here, that goes away, and what we're left with is just the height at time 0, the height when we start our clock. Okay, let's go into an example. So a rocket is launched upwards at 19.6 meters per second, so that's the initial velocity, from a 13.8 meter tall platform, so that's the initial height, so this is v sub 0 and this is h sub 0. And on Earth, acceleration due to gravity, again, is 9.8 meters per second squared. Construct the equation, that's the first part. So the position with respect to time, so this is, again, s is a function using time as its variable. Okay, so it's going to be negative 1/2 times the acceleration due to gravity, which is 9.8. And then we're going to have that times t squared plus the initial velocity, which is 19.6 times t, then plus the initial height, which is 13.8. Simplify this a little bit, and we get negative 4.9 t squared plus 19.6t plus 13.8. And this will parabola will describe the height, the vertical height of this rocket given the amount of time that it's been in the air. Okay, what is the initial height? Well, that is 13.8 meters. And where is that represented on the graph? Well, if we're plugging 0 in for t, so think of t as x, it's the horizontal axis. So if we're plugging in 0 for t, then this last number is going to be the y-intercept. So the initial height is shown as the y-intercept on the graph. So this is why we've spent so much time finding y-intercepts. It's because when you apply parabolas to real-world situations, the x and y axes actually tell you something about what's going on. And so the y-intercept in this case is going to be the initial height. It's how high the rocket is when we initially launch it. All right, when will the rocket hit the ground, and where is that represented on the graph? Well, let's actually start with the second question there. Where is that represented on the graph? So when the rocket hits the ground. So if we think about the rocket hitting the ground, that's when the height is 0. And when the height is 0, when the y value is 0, that's when we have an x-intercept. And so if we want to know when the rocket will hit the ground, we need to find, or I guess in this case, t-intercept, because our horizontal axis is time now. So if we want to know when it will hit the ground, we need to find the t-intercept. We need to find when the height is 0. And so what we can do is we can say 0 then equals negative 4.9 t squared plus 19.6 t plus 13.8. And then to solve this equation, well, you could either complete the square or use the quadratic formula. I'm going to use the quadratic formula because that's way easier. So then t is equal to negative 19.6 plus or minus the square root of 19.6 squared minus 4 times negative 4.9 times 13.8 all over 2 times negative 4.9. Now, since you should have a good grasp of the quadratic formula by this point, I'm just going to assume that you can work that through. The two values that you get then should be t is equal to negative 0.6 and t is equal to 4.6, and these would be seconds. Well, let's think about what's going on here for a minute. So if we have an x or t-intercept, so this is a time when it's hitting the ground that is negative. So what this is saying is that the rocket hit the ground 0.6 seconds before we launched it. Well, that clearly doesn't make any sense at all. So we can't have the rocket hitting the ground 0.6 seconds before we launch it and then have us launch it and then have it go up into the air. And so what's going on here is that basically when we take this mathematical structure, this parabola, and apply it to the real world, we have to kind of edit it in order to make it fit reality. And so, in reality, we have the rocket on a platform, so it's not hitting the ground before we launch it. So we have to throw that out. And furthermore, so let's actually take a look at what this graph is going to look like. So it's going to look something like this. So we have this initial height, and then we launch it into the air, and then it comes down. So you can see there's this t-intercept over here. So this is happening before we've even launched it. Well, we don't need to we don't need to look at any of that. That's all happening before we launch it. All we care about is what happens right when we launch it at this initial height. Then it goes up, comes down, and then hits the ground right here. And then also, so this parabola extends down, but anything down here is below the ground. So the ground is right here. This is a height of 0, that's the ground. And so all of this stuff, this is all underground. And so obviously, when the rocket comes, it's going to hit the ground and stop right there. And so we can ignore most of this parabola. In fact, the only piece of the parabola that we care about is this piece right here. So from when it launches to when it hits the ground, that's all we care about. And we just discard the rest of the parabola. We don't need it. And so part of that, we've just got to get rid of this negative time value because that just doesn't make any sense in the context of the problem. So this is when the rocket will then hit the ground. All right, question number 4. When does the rocket reach its highest height? So the highest height then is going to be the vertex, the extreme value. So that's going to be something up there, the vertex here. So if we want to know where the vertex is, well, If we want to know the time when it hits that, that's going to be the t-coordinate of the vertex, or think of it as the x-coordinate of the vertex, and that's given to us by x equals negative b over 2a. Now, for that, we're going to do, let's see, negative 19.6 over 2 times negative 4.9. Work that out, and you should get a t value of 2. And so that means that it's going to be at its highest height 2 seconds after we launch it. Question 5 says, what is the highest height that the projectile reaches? Well, if we know the time that it's at the highest height, then we can find the height just by plugging in that time. So we're going to find s of 2. So we're going to find the height, the vertical position, at a time of 2 seconds. So that's going to be negative 4.9 times 2 squared plus 19.6 times 2 plus 13.8. If you work all that out, you'll find that the height at a time of 2 is 33.4. So if we're going to graph this then, well, we're going to need to scale our y-axis a little bit. So we'll say that this is 8. We'll say that this is 16, and that this is 24, and that this is 32. And that'll give us a little bit better of a graph here that will actually fit on the graph. Okay, so let's graph the vertex first. So we were told that the vertex has an x value or a t value of 2, so we'll go over 2. And then up 33.4, so I'm not going to be terribly accurate here. It'll be about right there. And then we know that the t-intercepts are at 4.6, so there's 4, and then 0.6 is about right there. And then also negative 0.6, so that's about right there. But again, this one, for the purposes of actually figuring anything out for the graph, we're really going to ignore that because that's happening before we launch it. And let's see, we also know that the initial height is 13.8, so that's going to be, about right here. And then we could graph it from that. So it's going to come up, hit the y-intercept here, so this is really where we're starting our time. So then it launches into the air, hits its highest height, comes back down, and hits the ground. Now again, when we're actually applying this, we're going to ignore everything that's below the ground, and we're going to ignore anything that happens before we launch it. So we really just care about this part of the parabola right here.